Hello, welcome to the Project 4 demonstration video. Unfortunately, a letdown from other project demonstration videos. We run the library tests here, which mostly pass except for discrepancies in the disk block reads, but mine are more efficient than the references. fswrite fails in one instance. It's one of the indirect block cases. Unfortunately, just couldn't get that one working. And then fsremove also fails, possibly because fswrite is called, but obviously not guaranteed there. And then I don't know if this is required, but I'll just run the unit tests, which all pass fortunately. So from that, we can just move on to the code demonstration. So we have the open command, which generates a file descriptor, which is just sort of like an abstract indicator describing a connection with a file in the system. It uses the path of the file to find it and make that file descriptor, and then it records a mode in the command, which describes how the file can be accessed, whether it can just be read or it can be written. So how is that information actually stored? Well, there's just a file table on the system, which is just managed by the kernel, which just contains all the information about each file and its mode. And then that file table is connected to the inode table, which is part of the physical disk. The physical disk being comprised of the super block, which contains the metadata about the entire system. The inode tables, which contain the inodes themselves, which contain the actual underlying information about the files. And then the data blocks, which actually hold the byte streams, which correspond to the files. So once we make our character buffer in the second command, we can use the read command, which uses the file descriptor to find the blocks, and it does so in conjunction with the inode table. It can find the blocks in memory that you need to seek to get to the actual byte streams and blocks that make up the data that you're trying to read. So you can seek out those byte streams, and then you can actually read them, or you can write byte streams to the disk, and you can do that until the length of the read is 0 bytes, which means that you've read everything and your data is in the buffer. Once you have all your data read, you can close the file descriptor, which will just take away the connection between the file and the system. And so yeah, that's basically how that works. The errata and quirks, I pretty much already went over this, but yeah, the writing to the disk when there's indirect blocks involved is still up in the air. It doesn't work really. And then we also have the fsremove. It's possible that when a inode block is removed from the inode table and then you try to add in other inode tables, then undefined behavior may occur, unfortunately. What did I learn from this project? I definitely learned way more about the structure and organization of file systems, what the actual layout of the disk is, and how the disk interacts with the operating system to create persistence, one of the core 3 pillars in operating system principles. And yeah, it does that in many different ways. Yeah, there's no like one file system organization method, but yeah, it's both more complicated and more simple than it seems. On the one hand, it's all these hundreds of lines of code in this project, but at its core, it's just a few simple data structures that power the entirety of modern era storage. So that's pretty cool. So yeah, that about does it for this project. Couldn't really put the best effort forward because of a lot of other stuff going on right now, but hopefully, yeah, it's good enough.